बट हे पाठवलं ना मला सर. मी काय करतो तुमचे जर नाव टाकतो.
Hello. Hello.
Yes, sir.
Sir, can you listen me?
Yeah, you are audible, sir.
And what is the video quality?
Uh,
How is the video quality?
can you take camera some of offside so I can see your face clear? Yeah.
Okay.
Can you check your audio, sir? Sound?
Yes. Hello.
Yeah, it's correct.
You are very much audible to me.
Yeah, thank you.
And I'm not sure whether you can listen to me properly.
Yeah, I'm listening.
Okay.
One thing I want to request
Huh?
you guys, because you are sitting together now, so you have to mute your mic, both of you.
Yeah. We will mute ourselves
Yeah.
after our
Yeah.
role in the seminar.
Yeah.
How
Yes.
many have been joined on YouTube? Have you created
Yeah.
YouTube link?
So far,
How
39, sir.
Huh.
So far, 39.
In Zoom
Yeah. And
and on YouTube?
just now we share, sir. So we are going to share on Telegram group. So very soon
Okay.
we will.
Please share at the
Yeah.
earliest possible.
Yeah. We share in our chat box, sir. Zoom chat box.
Okay.
Share in our Telegram group, sir.
Has the principal joined? Sir?
Yes, sir. Yes.
Okay.
Yep.
Welcome.
Yes, sir. Dr. Zamdar sir, can you hear me? Dr. Zamdar sir, can you hear me? Please unmute your mic. Can you share brochure with me? Host केलं असतं sir.
Hello, Kansil sir.
Yes, sir. Yes, sir. You are audible, sir. Can you repeat, sir? Your voice is. Dr. S.D. Zada, sir, can you? You are not audible, sir. Please unmute your mic.
Okay, go ahead,
Yes.
sir.
Yeah. Now you are audible, sir. Yeah. Okay. Thank you,
Okay.
sir. Thank you.
I am unmuted now.
Yep.
हॅलो 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 आयरे सर हॅलो हॅलो
हा सर नमस्कार.
हां यूट्यूब लिंक आता मेलवरती पाठवली सगळी.
चालेल चालेल युट्यूबला जॉईन होतो. हो
हा नाही आहे याच्यावर जॉईन राहिलं तर काही अडचण नाही, वेलकमच आहे सगळ्यांचं. पण काही विद्यार्थी वगैरे असतील आपल्या तिकडचे सगळे तरी
हो चालेल
जॉईन होतील युट्यूब वरती.
चालेल
आणि
चालेल
याच्यामध्ये झूम ग्रुप चॅट मध्ये पण दिली लिंक.
चालेल. हो पाठवतो.
हो
हो.
चालेल.
Kushti sir.
Sir. Yes, sir. Yes, sir. Please unmute your mic, sir.
Am I audible now?
Yes, sir.
How many participants on YouTube?
So far 46, sir. On
YouTube.
and 15 on the YouTube, sir.
Okay, okay. Still,
Yeah, we are waiting. Yeah. Maybe in 10 minutes we will start, sir. Now,
principal sir have arrived.
yes, sir.
Okay, okay.
हॅलो कोष्टी सर. कोष्टी सर.
Yes, you are audible, sir.
हा सर. साहेब पण आल्यात. स्क्रीन ओपन करा आपली. वेलकम सर.
Okay, sir. चालेल.
सुरू करूया. लोकडे सर. बरं.
Hello, Dr. Kursi. Hello, Dr. Kursi, sir. Hello.
Yes, sir. You are audible, sir. Lokde, sir.
Okay.
Yes.
Shall we begin now? It's almost time 12 o'clock.
Yep. Yep. Sir.
Okay. Thank you very much. Dear participants, Rise Section Sanstha's DP Bhosale College, Koregaon, District Satara from Maharashtra, its Department of Physics and Internal Quality Assurance Cell organized international web seminar on recent trends in nanostructured materials, based devices and their applications in collaboration with Electra Solar Energy System, Private Limited MIDC Koregaon, District Satara. In such a gathering of stalwarts, I welcome you all on behalf of the Bhosale College Koregaon, and this international web conference is organized by Department of Physics on the most important and relevant topic entitled Recent Trends in Nanostructured Materials, Based Devices and Their Applications. I'm Dr. Lokde B.S., IQAC coordinator of this college. It gives me immense pleasure to welcome all the dignitaries, teacher participants, students in this gathering. In this web seminar, we are able to listen to the giant personalities from physics discipline. Honorable Professor Dr. B.R. Sanpal would be giving the inaugural talk, keynote address, and his resourceful talk, and it will be followed by the three resourceful talks by honorable resource persons, including Dr. S.D. Sartale from Professor, Department of Physics, Savitribai Phule, Pune University, Pune. And then after, we will be able to listen to Dr. Nilesh Sondankar, Assistant Professor, Department of Energy and Materials Engineering, Dongguk University, Seoul, South Korea. And the next resource person would be Dr. Amar Patel. He is a fellow at the Japan Society for the Promotion of Science, Hirosaki University, Japan. It means that we will be able to listen to the two personalities from abroad, that is Dr. Nilesh Sondankar and Dr. Amar Patel, and equally internationally reputed resource persons like Dr. B.R. Sanpa, who is Associate Dean, Senate Member and Professor, Vishwesvaraya National Institute of Technology, Nagpur, and Professor Dr. S.D. Sartale from Savitribai Phule University, Pune. Dear sirs, I wholeheartedly welcome you into this international web seminar. We have Principal Dr. V.S. Sawant. He is to give his welcome note during this seminar, and besides that, I am very happy to let you know that as per the registration data of this web conference, there are 1200 plus participants who have registered for this web conference, and which include honorable principals and other dignitaries also. The principals who have shown keen interest in their subject, and they have joined this gathering. Honorable Principal Dr. R.R. Ahire from Sakharvi College, Dhule, that is Khandesh region of Maharashtra state. Principal Dr. R.H. Patil from Shahada College, Nandurbar. Principal Dr. S.S. Kale from Dindori, Nashik. And another dignitary is Dr. Ankush Kadam, who is Senate and Management Council member of Dr. Babasaheb Ambedkar Marathwada University, Aurangabad. And I, on behalf of UP Bhosale College, Koregaon, Department of Physics and Internal Quality Assurance, say I welcome all these dignitaries in this e-platform of the web seminar on recent trends in nanostructured materials-based devices and their applications. And I am pleased to welcome Honorable Principal Dr. Sawant sir to give his welcome speech. I invite him, please, Principal Dr. V. Sawant sir. Over to you, sir.
Good afternoon to all. Distinguished guests, participants, dear colleagues, ladies and gentlemen. It is a true pleasure for me to welcome you to the international webinar on recent trends in nanostructure materials-based devices and their applications. Organized by IQAC, Department of Physics of DP Bhosale College, Koregaon, and in collaboration with Electra Solar Energy System Private Limited, MIDC, Koregaon. I am very grateful to Professor Dr. B.R. Sankpal, Professor VNIT Nagpur, Dr. S.D. Sartare, Professor Department of Physics, Savitribai Phule, Pune University, Pune, Dr. Nilesh Chondankar, Dongkok University, South Korea, Dr. Amar Patil, Hirosaki University, Japan, and all participant principals for taking time off from this busy schedule to inaugurate this webinar. Our college is established in 1968. We provide quality education in science, arts, commerce, computer application, and BHOC streams. At present, 3,460 students are studying in the college with 15 undergraduate and 7 postgraduate programs. Besides, the college offers career orientation certificate programs and short-term courses. Our college has been accredited A grade with 3.12 CGPA. It is also certified with ISO 9001:2015. I am especially honored to welcome you all on this digital platform of DP Bhosale College, Koregaon. The theme for this webinar is recent trends in nanostructure materials based device and their applications. As we all going through this pandemic period and with the fear of COVID-19, the inevitability of smart material is once again emphasized. PPE kits, gloves, goggles, and most unavoidable face shields, masks are the necessities nowadays. Many of these in variety of materials are available in market and also online. The trustworthy material needs trademark brand which can only be obtained only after a rigorous analysis. The topic of the webinar is shaped with what I mentioned. This created an opportunity for the participant to hear of the recent development in fields of nanostructure material-based devices. As we all know, the frequency of webinars all over the world increased so much that it is now very difficult to decide which webinar to attend. Still, in all, we have about 1,255 plus registrations from all over India and from abroad. I must appreciate the effort taken from our team. For the first time in this academic year, our faculty from the physics department has worked together to put an academic program that I am sure will satisfy everyone's requirement. On the behalf of Raj Shikshan Sanstha and DP Bhosale College, Koregaon, I welcome you all and wish very happy success for the webinar. Thank you.
हॅलो
Yes, sir.
लोकडे सरांना अनम्यूट करा. लोकडे सरांना.
Yeah, wait. Yeah, they can. Yeah, they can.
Okay,
unmute
thank you, sir.
themselves. Yep.
Thank you, sir. Thank you for such a nice introduction of this event. Now I have a pleasure to invite Dr. V.S. Jamdade, Head Department of Physics, DP Bhosale College, Koregaon, to introduce the special guest of honor for the inaugural function of this web seminar, Honorable Dr. B.R. Sanpasa. Dr. V.S. Jamdade, sir, please introduce the guest. Over to you, Dr. V.S. Jamdade.
Thank you, Lokde sir. Welcome to all. This international web seminar will be discussion and deliberation of bringing the gap between fundamental laboratory research and its application. Also, this web seminar will see the convergence of nanostructured material-based devices and their application bring together the scientific community of science and technology to discuss the latest development in the processing and characterization of nanomaterial-based devices and their applications. Nanotechnology has huge potential to provide technological solutions to many problems in a science, energy, physics, and environmental and medical fields. Eminent scientists will share their expertise with the faculty, researchers, students, and industrialists to promote the research in a basic and advanced applied aspect of the nanomaterial. The keynote and invited talks with the planetary and technical session, we will see the exchange of knowledge and information on the recent advances in a nanostructured material-based devices and their application, and ongoing trends in the nanomaterials and their application. It will be a great opportunity for interaction and collaboration between the academia and industry to extend the lab and pilot scale research in the nanomaterials to develop into innovative and cutting-edge technology for real development and solution. This web seminar will have session covering all the aspects of synthesis, characterization of materials and their application in a various sectors. Now, I invite and introduce the Professor Dr. B.R. Sanpasa. Dr. B.R. Sanpasa is a professor in the Department of Physics and working as Associate Dean and Senate member of Vishveshwaraya National Institute of Technology, Nagpur. This institute of national importance, he worked as head of the department and chairman of a board of studies in physics in VNIT. Also, he got the PhD from Shivaji University under the guidance of Professor C.D. Lokhande, sir. He worked as scientist at Helmut Center and Matter Institute, Berlin, Germany. He also worked as GSPS postdoctoral fellow at Gifu University, Japan. And he is a research associate in the University of Wisconsin, USA. He is a recipient of the Young Scientist Outstanding Work Presentation awarded by Material Research Society, Japan in the 2005 and by the Department of Science and Technology of the Government of India to participate in the meeting of Nobel laureate in Lindu, Germany in 2001. He has 134 publications with H index of 36, having the citation of above the 3,800. He has guided 13 PhD students to Dr. Sanpa received about 2.5 crores from the 7 major research projects from the DST, SERB, DA, BRNS, and UGC funding agency. As head of the department, he successfully received a DST-faced grant of 2.2 crores. He visited Sweden, France, Switzerland, Holland, Belgium, USA, Germany, and Japan for delivering the invited talk and meetings. He is fellow of Maharashtra Academy of Science, member of Institute of Physics London, the Indian Science Congress Association, India's Association of Physics Teachers, and Material Research Society of India. He is serving as expert committee of member of NAC and AICT. He is a VMC member, that is the eminent educationalist of Kendriya Vidyalaya. Also, he is a member of physics in RTMS University, Nagpur. Also, he is a member of Walchand College of Engineering of Sangli as a BOS member. Also, he is a VC nominated member at various colleges in the Maharashtra. He is serving as an expert academic audit for the Government and Autonomous Engineering College. He was nominated for the Shanti Swarup Bhatnagar Award in 2018 by the director of VNIT Nagpur. His research expert includes synthesis of nanomaterial, quantum dots, and nanowires and nanotubes of the organic semiconducting material by using the simple and low-cost chemical routes towards device grades development such as solar cells, sensor, and supercapacitor. This is the huge biodata. So I request to Professor B.R. Sankpa sir to deliver your keynote address and then your talk. Thank you.
I am audible?
Yes, sir.
Okay. Thank you very much for this nice introduction. And I wish to thank Principal Dr. V.S. Sawant sir, DP Bhosale College, Koregaon, Satara, and convener Dr. Vinayak Jamdade for organizing this recent trend in nanostructured materials-based devices and their applications. As we know that all world it is suffering from COVID-19, right? And there is a prevailing need to search for nanomaterial-based device which can have a wide application in medical field. And I feel this topic is well matched with the nanostructured materials for the base devices, which can be applicable for many devices. And here I am going to deliver that topic related to the solar cell, and some topics are there related to the energy storage application. And I feel this topic is much more suited that these devices may be applications in the medical field. So I wish to conclude for this keynote address so that all sessions can be started very soon. Thank you.
Hello.
Yes, sir.
So again, I will request to you, please deliver your talk.
Okay, thank you, sir.
Sir, mute करा, mute.
Okay, screen is visible. Hello.
Not yet, sir. Can you open your PPT, sir?
Okay. Now it is visible.
No, sir. Yes, sir.
Yes, sir. It's visible.
Yes, sir. Visible.
Okay. So as the topic of this conference, that is the recent trend in nanostructured material-based devices and their application. So in that concern, I wish to give the demonstration that the state of the art to develop energy conversion device by means of photovoltaic, and that is a colorful, and that is done through the smart nanomaterials. So you can think about how to use this nanomaterial for a different widespread application. And here I am concerning about the energy storage application, energy conversion application, and afterwards you can see some energy storage application. So this topic fulfills the things for this given title, that is the recent trend in nanostructured material based devices and their applications. Before going into the actual talk, just I wish to give some information regarding our institute. That is the Vishwesvaraya National Institute of Technology, that is VNIT Nagpur, which is only one institute that belongs to the central government from the NIT Council in Maharashtra. As this our institute, it is a national importance and it is a central government and autonomous institute it is there, and it is funded by MHRD. So in our institute, after qualifying the JEE examination, many students, they are entering for the engineering, architecture, and after BSc, they are entering for the basic sciences. So we are teaching to all branches of the engineering as well as the architecture, as well as we are teaching to MSc students. So these are the different branches are there in our institute, which pursuing BTech, MTech, as well as the PhD. And from the basic sciences, we have physics, chemistry, and maths, where we have MSc as well as the PhD students. For MTech and PhD students, we are providing fellowship from the institute as a teaching assistantship. And for PhD in basic sciences and this PhD in engineering, they should have GATE or NET qualification. Also, we have humanities department in our institute. So before going into this talk, just I wish to ask one question, that whether it is so complicated to work with nano. As this topic it is mentioned, nanostructured material for the device grade application. So you can think a little bit whether this nano it is much more complicated to work on, to apply something to produce your devices in the laboratory, so that finally it can go to the society, so that society can use these devices for different application. As for COVID-19, medical application needs energy conversion as well as energy storage devices. So we know that this sun, it is unlimited source of energy. Why we should not think to use this unlimited source of energy for conversion of the energy, that is the light to electricity by means of photovoltaic, that is called as a solar cell. So here I'm concerning about the application, that is the solar cell by means of photovoltaic application or photovoltaic devices. As you know that there are different photovoltaic devices are there, which are based on the silicon or copper, indium, gallium sulfide, or maybe CDS, CDT types of solar cell are there, or maybe indium phosphide, gallium arsenide type of solar cell are there. Right. Although in India, a lot of sunlight is available, but people are not that much using this type of solar cell, as the solar cell are little bit costly. So common people cannot afford this type of solar cell. So why not to think other solar cell devices? Yes, other solar cell devices which are cheaper, although if it is having lesser efficiency, no issue at all. But it should have a widespread area where that can be utilized. I think sharing is stopped. Hello. Hello. Sharing. Can you see PPT?
Yes, sir.
Yes, sir. Yes, sir. Continue. Sir.
Okay.
Continue.
Yes, continue, sir.
Continue, sir.
Okay. So here I wish to give the talk on the solar cell by means of the on the basis of the dye-sensitized solar cell, which can be possible to make the colorful solar cell. So whenever you are thinking for any application, maybe solar cell application we are concerning here, that you should think about 4 parameters. The first issue, it is the cost. So whatever devices you want to make, that should be at the lower cost. Whatever methods that you are going to use, that should be low cost and easily accessible. And whatever raw materials are there, that raw material should be easily available. For example, if you want to have the silicon solar cell, then you can have the silicon which are very pure, and in order to produce this silicon at very high purity, it is quite difficult, and you should have the clean room environment to produce this type of solar cell. And last option it is there, that whatever peoples are there in the society, they should use generously with the, and if it is having long-term stability and attractiveness, then it is a great. So before going to the basic concept of the dye-sensitized solar cell, we can know just how the simple solar cell, which is based on the PN junction, can work. As we have learned, this is in 10th, 11th or 12th standard, that P-type, N-type silicon can sandwich together to form the junction. And this is on the basis of energy band diagram, how this PN junction solar cell works. If we take this solar cell and illuminate with the visible light, then there is a generation of the electron and hole pair within the depletion region. This electron hole pair gets separated because of the built-in field. And this electron travels through the external circuit, and the cycle it is completed and electricity it is generated. And this is a simple way how we can understand the solar cell, which is based on the PN junction. But whatever dye-sensitized solar cell it is there, it is little bit idea is little bit different than the simple PN junction solar cell. So our approach to make the solar cell which are colorful on the basis of the dye-sensitized solar cell, whatever the process are there, that should be low cost and low temperature process it is there. And here I wish to concern about the zinc oxide, which is chemically deposited, which can have attractive affection along with sharp cut-in production. And whatever the process is there, that environmentally benign, and if it is flexible substrate that you are going to use, then it is having great application. So there are different points are there whenever you are thinking about the solar cell. If it is see-through, that is likely to be transparent. If it is flexible, great. If it is cheap, lightweight and colorful, then it can have many applications. So here I'm not concerning about the flexibility of the solar cell, but other parameter if it is possible to see whether it is possible to make the solar cell in the laboratory by using simple nano materials. So how this dye-sensitized solar cell works? This dye-sensitized solar cell construction is depicted here, as you can see in the block diagram. On the right hand side, there is a TCO that is called as a transparent conducting oxide. Glass means transparent conducting oxide, which is coated on the glass substrate. Usually FTO and TiO2 can be used to coat on the glass substrate so that you can make the glass upper layer as conducting as well as glass it is transparent, so that you can have a transparent conducting layer on which you have to coat the nano material. Usually TiO2 it is used for the dye-sensitized solar cell, and these are the P25 TiO2 nanoparticle which is procured from the Degussa company, and these are the interconnected nanoparticle with a very high surface area. The basic requirement for the dye-sensitized solar cell for this type of material is it should have the wide band gap. Means whatever visible light it is there, it should fall on the dye molecules which is coated on this nanoparticle, and this is a monolayer of dye which is coated on the high surface area interconnected nanoparticle network, and usually TiO2 it is used. Then you can place the liquid electrolyte and back contact as a platinum coated on the TCO layer. And this is just a block diagram in order to understand of this dye-sensitized solar cell. But on the basis of the energy band diagram, here you can see that this is a TiO2 where you can have valence band and conduction band it is there. Then you can have the dye where HOMO-LUMO it is there, and then liquid electrolyte. After illumination, this light excites the electron within the dye and it is transferred to the wide band gap conduction band. Means this electron it is transferred to the conduction band of the TiO2, and this electron travels through the external circuit towards the electrolyte, and this cycle it is completed and electricity it is generated. Here in a simple way you can see how this solar cell works. Then on the basis of this cross-sectional image of this schematic image of the dye-sensitized solar cell, after illumination you can excite the electron within this dye molecule. Here you can see that with the blue color, and it is transferred through the wide band gap semiconductor to the TCO glass through the external circuit and to the electrolyte. And this cycle it is simply completed and electricity it is generated. And this is a simple way how the dye-sensitized solar cell works. The highest record efficiency it was achieved in 1991 as a 11% with TiO2 by Professor Michael Gratzel. And till today it is reached to 12.5%. Means there is no much improvement in the device efficiency because of some limitations of this solar cell. So instead of this TiO2, we have thought to use zinc oxide, as the zinc oxide it is having similar property as that of the TiO2. He is a Professor Michael Gratzel who worked on the dye-sensitized solar cell, and a lot of work has been done, and industries are also working and they are producing this type of solar cell in the market, and these are available in the market as well. Then here I wish to demonstrate how we can make the laboratory scale solar cell by using simple nanomaterial. And here you can see the schematic that you can have a glass TCO. Then here one layer it is there. It is called as a compact layer or seeded layer. It may be there. And then you can have a very high surface area wide bandgap semiconductor. Then red color it is there, which is for the coating of the dye molecules on the high surface area. Then electrolyte and back contact. Then these are the stepwise development. That is the TCO layer. It is there that can be used as FTO or ITO. Then here I am considering about the zinc oxide. So I called as a seeded or flat zinc oxide, then nanoporous zinc oxide, then sensitizer dye, and then liquid electrolyte and back contact, and then finally device testing. So here for the TCO, what we have used the laboratory made FTO, which is made in the laboratory by using simple spray pyrolysis technique. So these are the parameters that we have used for the TCO to form this FTO. And here you can see this is a glass and this is a FTO, and the transparency, it is not so much high, but it is 93%. And here in the cross-sectional image, you can see it is less than 500 nanometer, and the sheet resistance is a little bit high, 15 ohm per square. But still in the market, you can get now the sheet resistance, it is below 5 ohm per square. Right, and transparency now it is possible to achieve about 99%. So how to synthesize this zinc oxide and why we have chosen this zinc oxide? Usually P25, that is from the Degussa TiO2 is used for this type of solar cell, and which is firing at 450 degrees Celsius after coating on the FTO coated glass substrate, and then dye adsorption and then drying. But whenever you want to use the low temperature process, then there may be a problem of insufficient necking between the particle. And firing at 450 degrees Celsius, it is a very high temperature. So if you want to possible to reduce this temperature to maybe lower down to 100, then it is great, because in order to have the flexible substrate, you can use PET, that is a FTO coated PET as a plastic substrate, so that it is possible to bend this type of solar cell, so that you can make the flexible solar cell as a device in your hand, so that it can have a wide application. So why we have chosen zinc oxide instead of TiO2? Because the energy band diagram, it is the same as that of the TiO2. But if you see the electron mobility, it is very high as compared to the TiO2. But chemical stability is very low of the zinc oxide, and we have taken this as an advantage to synthesize the zinc oxide at lower temperature as compared to the TiO2, which is used at very high temperature, that is 450 degrees Celsius, and we have tried to reduce the temperature below 200 degrees Celsius, and we have tried still to have below 100 degrees Celsius, but we have not succeeded to do that one, but still we have achieved up to 200 degrees Celsius to have your zinc oxide on the TCO layer. So how we have deposited this zinc oxide? So we have used simple chemical method, that is the chemical bath deposition, where cationic and anionic precursors are there, which are placed together. And another method we have used as a sealer, which is a modified method of this chemical bath deposition, that is called as a successive ionic layer adsorption and reaction, where you can place cation and anion separately instead of putting together. So here there are two types of zinc oxide we have used. One is called as a compact or seeded zinc oxide, which is used as a blocking layer, because in this type of solar cell, we are using liquid electrolyte, and this liquid electrolyte, it can have the contact with the FTO coated glass substrate, and your device can be get shortened, right? Because you have porous zinc oxide with a very high surface area. In order to avoid this one, we have used a compact or seeded zinc oxide by using simple sealer method. So first I wish to demonstrate how we have used this sealer method. As this sealer, it is based on the separately placed cationic and anionic precursor solution, and you are dipping of the substrate into separately placed cationic and anionic precursor. So we have taken FTO coated as a glass substrate and then dipped inside the zinc acetate solution, which is complex with ammonia. Then there is an adsorption of the zinc ion on the substrate surface. Then for the anionic solution, what we have used? We have used simply water at 80 to 90 degrees Celsius, which is kept on the hot plate. It's just boiling water on the hot plate. So we have taken the substrate, which is adsorb, zinc ion adsorb, and then we have dipped inside the anionic solution, where there is a reaction with cation and anion, and there is a formation of the zinc oxide and hydroxide on the FTO coated glass substrate. But for the dye-sensitized solar cell, you need pure zinc oxide. So it should be free from the hydroxide formation. In order to get rid of this hydroxide, what we have did, we optimized the annealing temperature and we have dropped down to 200 degrees Celsius. So we have annealed that one film at 200 degrees Celsius for 1 hour so that you can get pure zinc oxide on the FTO coated glass substrate. And this is the X-ray diffraction pattern where you can confirm whatever obtained zinc oxide is having what structure. And we found that it is having hexagonal ultra structure of this zinc oxide having orientation along 002 plane. That is the C-axis orientation. In the SM image, you can see this is a seeded layer of the zinc oxide which is grown on the FTO coated glass substrate. And you can see the growth, it is perpendicular to the substrate surface, that is the C-axis orientation, it is there. Right, and this we have used as a seeded zinc oxide, which is not really compact, but we can say that it can create some nucleation sites for the further growth of the nanoporous zinc oxide. So next, nanoporous zinc oxide, it was deposited by using simple chemical bath deposition, where you can put the cationic and anionic precursor solution. So this is a simple chemical bath deposition technique where you can place the cationic and anionic precursor solution together, right? And then you can use the stirring or without stirring, right? Then what we have used simply zinc acetate with hexamethyl tetraamine, and the deposition temperature was just room temperature, that is 28 degrees Celsius. The deposition time, it was varied from 20 to 40 hours for the optimization. Then after deposition, this film also annealed at 200 degrees Celsius to convert the hydroxide part to, that is to remove the hydroxide part from the deposited film. And this is the photo image of the zinc oxide where we can see that this is a white in color of this zinc oxide which is deposited on the FTO coated glass substrate. That is prior deposition of the seeded zinc oxide is there, which can act as a nucleation center for this growth of the zinc oxide. But for the dye-sensitized solar cell, you should have the zinc oxide with a very high surface area, right? And before that one, we have done some characterization to see whether what type of zinc oxide it is there, and we observe that it is also having hexagonal Rosa structure. Then one criteria for the dye-sensitized solar cell that your film should have the wide band gap. So in order to test the wide band gap of that zinc oxide, we have taken absorption against the wavelength, and we have calculated the band gap value by plotting alpha h nu square versus h nu, where we can see that the band gap, it is more than 3 electron volt. Means whatever visible part of the solar spectrum it is there, it can pass through this zinc oxide. But the another criteria of this zinc oxide is that it should have very high surface area. So what we have done, we have taken some surface morphological image of this zinc oxide, and this scale bar here, you can see that this is a 2 micrometer scale bar, it is there, and this is a petal-like morphology you can see on the of the zinc oxide. But here it is not clearly visualized whether this zinc oxide is having very high surface area or not, and interconnection of the nanoparticle, it is there or not, it cannot be clearly visualized. So in order to get the clear insight, so we have taken the high resolution SEM image, and here you can see that this is scale bar, it is 100 nanometer, right? With a very small scale bar, here you can see clearly how these nanoparticles are internally connected to each other. And this is having very high surface area. And this morphology is analogous to the cactus-like morphology. So you can say that this is a zinc oxide with the cactus-like morphology, which is having very high surface area, which is the basic need for the dye-sensitized solar cell, on which you can coat the 1 monomer of the dye molecules on this wide band gap zinc oxide. So this is a cross-sectional image of the zinc oxide where you can see the thickness of the zinc oxide, and also we have tested with the wettability test whether it is hydrophilic or hydrophobic, right, of the zinc oxide, and we observed that this shows 56-degree angle, which is hydrophilic in nature. So there is a possibility to adsorb this dye from the aqueous as well as the non-aqueous solution, right, from the dye to adsorb on the zinc oxide. So all these parameters are listed in this GelCom paper, so that not only this cactus-like morphology, you can get different morphology of the zinc oxide, maybe hexagonal, petal-like morphology, or nanobeads type of morphology, and all these parameters are included inside this paper, where we have used simply CLR and CBD method to get different morphology of the zinc oxide and having different precursors like zinc acetate, zinc nitrate, zinc chloride, zinc sulfate, right? Just by varying this precursor solution and combination of the CBD and CLR, you can get different associated morphology of the zinc oxide by using simple solution chemistry, which can have a wide application. So the next step it is there, that is the dye adsorption. So 1 monomer of the dye has to be adsorbed on the high surface area of this zinc oxide. And then we have used the ethanolic solution of the dye molecule. Then we have used liquid electrolyte, that is the polyiodide liquid electrolyte. It is used, which is placed between the dye-coated zinc oxide and platinum as a back contact. So it is used capillary action to place this liquid electrolyte inside these two cathode and anode as a electrodes. So initially we have used evosin Y as a dye to adsorb on the zinc oxide, which is a red in color. But for the evosin Y, it is having very low absorption in the visible part of the solar spectrum, so that you can see that it is having absorption against the wavelength, that is 500 to 550 nanometer, means it is having very low absorption in the visible part of the solar spectrum. Whenever you want to use TiO2 for this dye-sensitized solar cell, you need dye which is having NCS group, which can attach very well with the zinc with the TiO2. But whenever you are thinking about the zinc oxide, you should have the dye with the carboxylic group, which can attach very well with the zinc oxide. So we have used evosin Y dye, which is having this carboxylic group, that is COOH group, which can attach very well with the zinc oxide. And this is the zinc oxide film. Initially, it was white in color, and then after adsorption of the evosin Y dye, you can see that this is a red in color. So that this is the evosin Y dye adsorbed zinc oxide with the red color. So by using this one, you can fabricate the red color solar cell. So what we did, we have assembled this device by using platinum as a back contact, then polyiodide as a liquid electrolyte, and then we have optimized this device. And here in the inside image, you can see that there are only 2 crocodile pins are there, means there is no perfect sealing that we have used. And this, we fabricated this type of solar cell. And we have optimized different parameters like concentration, time, CLR cycle, dye concentration, iodine concentration, solvent, right? And we have tackled with the efficiency and the current density. Here you can see this is the current voltage characteristics which is seen for the solar cell, right? And you can see that the efficiency we have reached about 2%. Means for silicon or gallium arsenide type of solar cell or CDS CDT type of solar cell are there, the efficiency is very high, no doubt. But cost issue is very high. But for this type of solar cell, although efficiency it is less, but cost issue it is drastically less than the silicon type of solar cell, where area is not a problem. There you can use this type of solar cell based on the dye-sensitized solar cell. Then all these results are published inside the Solar Energy Journal, where you can get the idea about how to adsorb the dye, how much time it is there, right, and how much efficiency can be possible to achieve. And these are based on the influence of the processing parameters on the chemical grown zinc oxide by using low cost evosin Y dye. As this dye, evosin Y dye, it is there, it is very cheap dye. For example, for 25 gram, you can get it about 700 to 800 rupees of this dye. And this dye, it is low cost as compared to the ruthenium based dye, which is usually used on the TiO2 layer, which are very costly dyes are there, and these are easily available in the market. And we are using micromolar solution of this dye. Means this what type of solar cell fabricated? It is very cheap solar cell as compared to the silicon solar cell. Then in order to get higher absorption, what we have used? We have used another dye, that is the D149 dye, which is also having carboxylic group. And it is having wide absorption than the evosin Y dye, and we have achieved the efficiency about 3.5%, and area we have used as a 1 centimeter square. That is for the large area. So these results are also published inside the Material Literature journal with the efficiency 3.5%. Not only this one, we have done some colorful approach. That as you can see the solar spectrum, it is having blue color, yellow color, red color. Then we thought that why not to produce different colorful solar cell so that you can have a different solar cell with the different colors in your hand. So what we have used for red color evosin Y dye, which is having carboxylic group, then coumarin 343, which is a yellow color, which is having carboxylic group, but we have not received the blue dye, with the carboxylic group, but we have another dye that is the methylene blue, but having chromium group. So these are the film which is adsorbed on the zinc oxide, where you can see that red color, yellow color, and blue color it is there. This is the absorption against the wavelength spectra. It is there. This is for coumarin. This is eosin Y for, and this is for methylene blue. Means it is each dye it is having each absorption region in the visible part of the solar spectrum, and depending upon its absorption, it can show the different efficiency. And we have seen the coumarin dye, it gives the efficiency about 1.16%. Eosin Y we have just seen, that is about 2%, and methylene blue it is 0.02%, because this is not having carboxylic group, it is having just chromium group, although it is having very high absorption in the solar spectrum, but it shows very less efficiency because of the non-availability of the carboxylic group, which can attach very well with the zinc oxide. So we made some advanced colorful approach, that we have three dyes in our hand, that is, one is eosin Y with the red, then you can have the yellow, that is the coumarin 343, and methylene blue with the blue color. So we can have a red, yellow, and blue. If you mix red with yellow color, you can get the orange color. If you mix the yellow color and blue color, you can get the green color. If you mix the red color and blue color, you can violet color. This by just mixing the different dye, it is possible to generate different type of colors and different type of solar cell. So just we have tried with the red and yellow to get the orange color, just by mixing, just by chemical mixing of these two dyes. And this is the two dye mix which shows the orange color, which is adsorbed on the zinc oxide. And the beauty here it is that if you mix these two dye, that is the yellow dye and red dye, right, you can get the coverage in the yellow part as well as the red part. Means whatever this mixed dye it is there, that is the called as a cocktail dye, which covers the both part of the solar spectrum from yellow as well as from the red. And this is just the absorption of the dye. And here you can see the next image it is there, that is the quantum efficiency. That is incident photon current conversion efficiency. If you illuminate with the one electron, how much one light photon, how much electron it is generated. And here you can see that, yes, this is the quantum efficiency. Yes, it is visible.
Yes, sir.
Yes, sir.
Okay.
Yeah,
Okay.
it is visible, sir.
Yes, it is a quantum efficiency against the wavelength. This is for the completed device. Here you can see that this completed device also covers the both part of the solar spectrum from the yellow as well as from the red dye. So this is the efficiency of the cocktail dye, which shows the enhancement in the efficiency, not so much high, but it is better than eosin Y dye, and it is reached to 2.25% just by mixing two dyes. Not only this one, we have tried different dyes like rose bengal, rhodamine B, mercury chrome, D149, N799, which is adsorbed on the zinc oxide. As each dye it is having its own absorption in the visible part, it shows the different efficiency. But the beauty is that you can produce a different colorful solar cell. And these are the dye adsorbed zinc oxide by which you can fabricate the solar cell in your laboratory, which are colorful in nature. So one paper it was published, that is the basic idea with the advanced approach, that efficiency boost by sensitizing blended dye on the chemically deposited zinc oxide, which can show the colorful approach of this type of solar cell. Because up till now you have seen the solar cell which are either black in color or maybe blue in color, but it is possible to fabricate red color, yellow color, green color, this type of solar cell, right? So what are the applications are there? Here you can see that this was appeared in the Lokmat as the first front news, that is Saur Urja Ata Swastat Mast Rangit Gatatun. And this whole work it was carried out by my student Prashant Paviskar. So what achievements are there? We have run the digital watch as well as a scientific calculator by using this type of solar cell. So idea is that by doing the research, that research should be applicable to the society, one thing. You can get the research paper, no doubt, but whenever you are using this type of materials to fabricate the device which can have a direct application for the society, you can get the satisfaction. And if your device is working well, then you can have a very high satisfaction just instead of publishing just only in the journal. So what we have done, that as this eosin Y dye gives this red color solar cell which shows the output voltage of 0.5 volt. That is, we have connected three devices in series. For this digital watch or calculator, we need 1.5 volt, and we have connected in series. right? And this is for digital watch and this is for the calculator. And we have tested this one for almost 2 months without perfect sealing, just by using simple crocodile pin. If you have perfect sealing, this type of solar cell can work for 5 to 6 years. But there is of course, degradation of the dye may be there. That's why its lifetime is not very high, like a silicon solar cell. So here you can see that how this solar cell works. This is in the dark and this is in the light. And this is the how device it is working. So here you can get the clear idea that lab-made device can be possible to demonstrate that you can get the better satisfaction that your device is working well. And here we have produced, here you can see just we have used a crocodile pin without any perfect setting. Still this device, it is working well. And we have run the calculator by using lab-made device. And these are the application. So whatever colorful solar cells are there, it can be used for the dual purpose. One, for the light to electricity conversion. And second one for the attractiveness. So that whatever color it is there, which is in contact with the sunlight, that is possible to replace with this type of solar cell, where this solar cell have the dual purpose. One is light to electricity conversion and second one is for the attractiveness. For example, roof tile, you can have brown color, or maybe carport it is there, blue color, your car it is there, yellow color, right? For example, this building you can see this is blue color, or this house it is painted. Instead of painting, you can use this type of solar cell. So where you can have the attractive application along with sharp cut in production cost, although efficiency may be low, we can generate the electricity by means of this type of solar cell. So here you can see that not only this one, for example, truck it is there with the blue color or yellow color, and this truck it is running on a road because it is always under the sunlight, right? So this type of solar cell can be used for this type of application, so that you can generate the electricity from this type of solar cell as well as the attractive application. So we can say that this nano can play a very vital role for the energy and environment through the soft solution chemistry. So we can work against the global warming, and this type of devices are there which can be having direct application for the society, so that you can make the devices by using simple nanomaterials in the laboratory, by using simple solution chemistry where there is no necessity for the very high sophisticated instruments.